potential energy of an electric dipole placed in uniform electric field. Let us consider a uniform electric field capital E. This is the direction in which uniform electric field acts. In this uniform electric field, let us imagine an electric dipole of charge Q and length 2a is placed. Let this be charge plus Q and this be the charge minus Q. We know when a charge is placed in uniform electric field, plus Q charge experiences a force plus QE along the direction of electric field, and minus Q charge experiences a force of minus QE in direction opposite to electric field. Plus Q charge experiences a force of plus QE in the direction of electric field, and minus QE is the force experienced in the opposite direction. And these two forces are equal and opposite. They are two equal and unlike parallel forces, and they have different lines of action, hence they constitute a torque on this dipole. And we know the torque experienced by the dipole is equal to PE sin theta, where theta is the angle between the direction of dipole moment. This is the direction of dipole moment. Always dipole moment act from negative Q to positive charge. Negative minus Q to plus Q charge. This is the direction of dipole moment. This is the direction of applied electric field. Between P and E, the angle is theta. If it is so, the torque experienced by this dipole in uniform electric field must be tau equal to PE sin theta. Now just imagine we rotate the dipole through a small angle d theta. Let d theta be the elementary angle through which the dipole is rotated. This is also d theta. Now if the dipole is rotated, definitely the work has to be done. And we know the work done for rotating through an angle d theta is dW, which is equal to tau d theta. Already we know tau is equal to PE sin theta. Substituting from equation 1, let us write dW is equal to PE sin theta into d theta. This is the elementary work done for rotating through an angle d theta. If it is so, on rotating through an angle theta, let W be the work done, which is the integration of all these dWs, all this elementary work done. Now, what is dW? That is P E sin theta d theta. On integrating, we can get the total work done W, and that is equal to, we are integrating over the angle. So if we write from 0 to theta, then we can write this as PE into integration from 0 to theta of sin theta d theta. And already we know in calculus, integration of sin theta d theta is minus cos theta plus constant of integration. We consider this as constant of integration as 0 here. Hence, the work done in rotating the dipole through an angle theta is minus PE cos theta. And this work is stored in the dipole as its potential energy. So potential energy stored in the dipole on rotating through an angle theta in the electric field will be minus PE cos theta, or it can be written as minus P dot E, where P and E are the vector quantities. So this is the expression for total energy, which is the potential energy stored in an electric dipole placed in uniform electric field. Now let us see when angle theta, different cases let us consider. When angle theta equal to 0, that means when the dipole is parallel to electric field. This is the dipole moment P, and this is the electric field capital E. When these two are parallel, potential energy of the dipole must be equal to minus PE cos 0, cos 90 0, cos 0 1, which is equal to minus PE. Similarly, when angle theta equal to 90 degree, this is the electric field and this is the dipole moment. Here dipole is aligned perpendicular to the electric field. So this angle is 90 degree. So when angle is 90 degree, potential energy of the dipole must be equal to minus PE cos 90. Already I told you cos 90 is 0. Hence potential energy stored will be 0. Similarly, when angle theta is 180 degree, theta 180 means the electric field is acting in this direction. This is the electric field. And the dipole is making an angle 180 degree, which means P is anti-parallel to the electric field. This is P, this is E. So here P is anti-parallel to electric field. In such case, potential energy of the dipole is equal to minus PE cos 180, cos 0 1, cos 180 is minus 1, hence minus 1 into minus PE must be plus PE. You can see when theta equal to 180 degree, potential energy is maximum.